Our third plenary session today is going to be taken by Simon Box. And without any further ado, I think I'll just pass it over to you, Simon, and I will just trust that you'll finish within time for us to have a few questions at the end.
I'll do my best. Thanks very much, Stephen. Okay. So today I'm going to talk about machine learning strategies for Signalized Junction Control. Actually, the first presentation I ever gave on this project was UTSG last year, so it's really nice to be coming back and doing a plenary slot to update you on what I've been up to. So I'm going to launch straight into it. And to start off with, before I get into explaining the nitty-gritty of what I mean by machine learning strategies for junction control, I'm going to talk to you about a computer game that we've developed at the University of Southampton. Some people may recognize the director of TRG here, Nick Hansel. He is my personal favorite guinea pig for playing this computer game. So what Nick's doing here, and you'll see why that is in a minute, what Nick's doing here is controlling a signalized junction, a simulation of signalized junction from SciAS Paramix software. He is basically viewing what's happening on screen and choosing which stage to select by keyboard input. So I'm sure you realize in a signalized junction the traffic lights can be configured in a number of stages, and only one stage can have the green light at any one time. So Nick's basically choosing which stage to give the green light to. Now the fun thing about this is that we can collect statistics and evaluate how good Nick is at controlling a junction. And this is Nick's high score, if you like. So the delay is, as I'm sure you realize, the delay to a vehicle, how much it's delayed getting through the junction, averaged across all vehicles for Nick when he plays this game for a simulated hour is just, just under 14 seconds. Now, of course, this isn't any fun by itself, so you can see how does somebody else do? Well, I had a go myself. Nick has many years' experience, I should say, controlling junctions. I, on the other hand, have grown up during the computer game generation, so I thought maybe, this might give me an edge, but unfortunately, low is better, of course. Unfortunately, Nick beat me by a good half a second or so. But of course, when this is really interesting is when we compare our performance to the performance of the algorithms that are out there today controlling junctions. So one such algorithm is MOVA, which is commonly used in the real world on isolated junctions. It uses inductive loops in the road to detect the presence of vehicles, and we can simulate those loops in Paramix, and we can analyze the performance of MOVA. So the delay on MOVA is best part of 20 seconds here. So you can see that Nick and I have done much better. But, what I should stress here is this isn't really a fair test, because, as I said before, MOVA is just collecting counts of vehicles at specific points. Nick and I have a lot more information because we can see all the vehicles on the computer screen. So in principle, we know the position and speed of all vehicles. But, in transport research, we're always looking to the future. And we can consider a future, the utopian future, where all vehicles are driving around with GPS and Wi-Fi, and they can transmit their position and speed to a signalized junction. And in fact, this is something that's been looked into, and control algorithms have been developed. We've done some ourselves at TRG. One of our best ones is an algorithm called hybrid auctioning agents. I won't go into explaining that, but I'll just show you how it performs. Again, it's got a big advantage over MOVA, so as you'd expect, it outperforms it. But what's really interesting is it's still not as good as Nick Hansel. And what this says to me, and what this should probably say to you, is that if you aren't already thinking of signalized junction control as an artificial intelligence problem, then you probably should be. It's got the classic conditions that you are perceiving things about the environment, about the state on the road, and you want to use that information to make smart decisions. It's something that apparently humans can do quite easily and intuitively, but it's more difficult to get a computer to do. So I'm going to talk about some artificial intelligence approaches to signalized junction control, specifically to machine learning junction control strategies that we've developed at TRG. Now, the first one of these is supervised learning. This is learning from a teacher. This is where you have an example of good control already, and you try and design an algorithm to emulate it. Now, just so happens we do have an example of good control. Nick here, playing our computer game. So we can design an algorithm that will observe Nick playing the computer game and try and emulate his performance in the future. So just to explain how we do this, I'm going to quickly summarize how you might want to think about a conventional control algorithm. So conventionally, we would have some variables on the right here that describe the state, i.e. what's going on the road right now. Those variables would be passed into a control algorithm where there would be maybe some traffic theory, maybe what the designer of the algorithm just thinks is plausible behavior, maybe some parameters tuned to historical data, and you crank the handle, and out the other end comes a decision. And in this case, the decision means that at this time t, which stage of the junction should have the green light. Okay? Now, there's quite a nice little way we can visualize what this algorithm's doing if we consider a very simple situation with just two variables in our state. Every possible state that can be existing on the road is defined as a point somewhere in this two-dimensional space. And for every point, there is a corresponding stage, which is the decision that that control algorithm would select for that point. So I've done 3 stages here. The number's arbitrary. But as you can see, you can create a map. It's essentially your control algorithms are mapping from states to decisions. And you can visualize it something like this. So under the machine learning approach, we start with a blank state space with no mapping, and we use evidence of what we think is good control to work out the best way to divide the space up. Okay. So before I just explain how that happens, I need to say, what are our variables? How do we describe the state? Well, I've already mentioned our high bid auctioning agent algorithm, which we simulate as receiving GPS data from all the vehicles in the simulation. We do the same here with our machine learning approach, so we can compare it against the high bid algorithm fairly. And we could just take that raw data to define our state, but then we'd have a very complex, high-dimensional space to deal with, so we simplify it quite a lot. This is a schematic of the signalized T-Junction that Nick's controlling. The roads that approach the junction, we've divided up into zones or areas, which I've labeled here. If you just consider one of these areas, all the vehicles in that area transmit their speed and position to a software agent which monitors that area, which then uses that information to calculate a bid. Now, a bid is a single scalar number which just tries to say how bad things are in that zone right now. Or another way of saying that is, how strong is the need for priority? So at any time, all these 4 zones will be transmitting their bids to a junction controller. So as far as the junction controller is concerned, the state now, what's going on the road right now, is defined by these 4 numbers, these 4 bids, and they define a 4-dimensional bid space, or state space, sorry, which we need to divide up into decisions. Now, I'd love to be able to show you some visualizations of this 4-dimensional state space, but unfortunately, the Open University have only provided us with a 3-dimensional lecture theatre. So what I'm going to have to do is present a toy example with a situation where we just have 2 bids. Okay, so imagine a very simple junction. We've only got 2 zones, 2 bids, and we've also got 2 stages. And we are monitoring a human expert who's controlling the junction. So let's say every time the expert chooses stage 1, we plot a red point. And every time the expert chooses stage 2, we plot a blue point. And as you can already see, we now have some information which might tell us how to divide this space. What we really want to know here is when we get a new state in the future, what's the probability that the expert would have picked the red stage, or the probability they would have picked the blue stage? So hang on, I've got a little bit of an animation going on here. So what we can do is we can rotate this space and add another axis for probability, and we can rearrange these points. We'll call this the probability that the expert picks the red stage. So we've got some data which we know has probability 1, so we put that up there. The rest we know has probability 0. And our task is to fit a probability function across this space, okay, that fits these data points and tells us for the entire bid space, the entire state space, what is the probability the human will pick red. And we do this using a tool called a neural network, which is very commonly used in machine learning problems. And we get something like this for that data, particularly there. So this is giving us the probability across our bid space, or our estimate, I should say, probability across the bid space, that the human will pick the red stage. There's a corresponding curve for the blue stage, which is just the inverse of that, because obviously everywhere in the space, the probability needs to sum to 1. So we can look at this from another angle. If we just look at this from above as a contour plot, The only thing we're really interested in is the line where the probability equals 50% that you would pick red stage or blue stage. This is the decision line, and we can just pick that, find that line, colour in the difference, and then we've got our map. This is our strategy now for controlling the junction. Okay, so when we take this and we apply it, we get Nick to play the game, we train our neural network, and then we use our neural network to control the junction, and we can match Nick's performance. Okay, so it works. But this is quite a simple case. We're just looking at a simple isolated T-junction. We've got a constant level of demand. It's quite an easy problem. But we can crank up the complexity a bit. This is a network containing 2 junctions in Southampton. And the video you're watching is of it being controlled by a neural network after it's been trained by me in this case, because Nick wasn't around. Now, the interesting thing about when you have junctions close together like this is advantageous, or often advantageous, to coordinate the action between them. When we use the neural network control, we don't explicitly tell the algorithms to coordinate these 2 junctions. But when I'm playing the computer game, I try to coordinate it where I think it's necessary. And hopefully that information comes out in the wash. And if you watch the video, you may see some instances, when it's busier at least, that some vehicles drive all the way through from left to right or vice versa. So we can also control this junction with our high-bid algorithm. Incidentally, our high-bid algorithm does explicitly coordinate the control between junctions, and then we can compare the performance of that and the neural network trained, in this case, by me. So before I showed you a single statistic for delay averaged across the entire test. Here I'm showing you delay again, but we're looking at it, how it varies through the test. This is more interesting here because we're varying the demand, basically the amount of vehicles that we're pumping into the simulation. And you can probably see from these delay traces that there's peak in demand after about 1 hour of testing and also about 3 hours of testing. And what you can see is that, again, we've got the neural network, the trained neural network outperforming the high-bid algorithm. The average across the whole test is by about 2 seconds. And you can see that the majority of this is in the peaks. These peaks here are the points where the road is at its busiest. And that's when the trained neural network really performs. So delay is one statistic, probably the most interesting statistic, or the most informative statistic you can look at, but it doesn't tell you the whole story. Because we also want our junction controllers to be fair. So you could potentially have a situation of low delay where 95% of your vehicles are getting through very quickly, but some vehicles are getting severely penalized and waiting around for a long time. This isn't something we want to see in the real world. So a way that we can judge this is by looking at the journey time histograms, the distribution over journey times for a test. So the top distribution is high bid, and as you can see, we have a lot of vehicles getting through very quickly in the 30 to 40 second range, but this also has a bit of a tail and plenty of outliers. In fact, there are some that are off the scale, and one poor unlucky vehicle gets stuck in this simulation for about 10 minutes. The neural network control, by comparison, doesn't have so many vehicles getting through fast. Its peak is in the 40 to 50 second range, but it has a very tight tail and very few outliers. It's also, just as a point of interest, it's a nearly perfect fit to a log normal distribution. So that's one type of learning, supervised learning. But is it really the best we can do? One problem that may have sprung to mind already is that we are making the implicit assumption that every decision the human makes is a good one. We know that that can't necessarily be the case. But hang on, right? We are assuming we've got GPS in all our vehicles and we're receiving all this data. So surely we can, in principle, evaluate whether our decisions are good or bad and feed that information back in. And the approach to doing that is known as reinforcement learning. This is learning on the job, learning through experience.